I'll probably be alright with it. So while we're waiting for a couple of people, I've presented in this room a few times, and you have these handy metal legs. So if you keep an eye out, I'm definitely going to go like this at some point. So I'll apologise now.
I'm going to stand in the doorway because I'm going to introduce two rooms at once. So just a little hello and introduction for myself. I'm James Moore. I'm one of the Oak Table founders, and I attempted to organise the agenda for today, which is already turning into a bit of a debacle, but we'll see how it goes. So logistically, the only thing you need to know is there's 2 sessions, some food, 2 sessions. There might be less than 2, that's the next point. Chris Antognini is not going to make it, we don't think, because his flight's been delayed 2 hours already. He's already tired, and I think it's now terminally tired. So I don't think he's going to make it, and Kurt is also running late.
Yeah.
If he's here, then that's great, but if he's not, we'll do a little reshuffle, and Julian might go up and swap places with him. So that's about where we are. So enjoy the first 2 speakers, Melanie Caffrey over in here, and Bernie Dugggs over in here. Thank you.
Okay. Thanks, James. I almost said good morning, it just feels like morning, right? Good afternoon, and I'll kick off by warning you that a man shouldn't feel this bad without alcohol being involved, okay? So I have a very, very bad flu, so when I get to the end, then the alcohol will be involved. It's medicinal. Okay, so what I'm going to talk about today, this was James's suggestion, was I used to be a ZX Spectrum games programmer and used to write commercial games. And what you'll find is that a lot of members of the Oak Table are about the same age. And not so much now, we're starting to get some young blood and there's women and everything, right? But there's a lot of guys about our age. And we've often discussed how, I think the reason that we all got into this was people were more passionate about computing when we got started, okay, about the machines and you could do more and this kind of thing. So James suggested that, and he wasn't sure I'd do it, whether I'd do a nostalgic talk about ZX Spectrum games programming. So that's what this is about. So who am I? This is a brief history of my games development. Well, not really. So around about 1980, when I would have been 14, something like that. Wow, that's a weird sound effect.
Doug, you might want to just clip the mic on your t-shirt rather than on the neck. As high up as you can, but not actually on the neck.
Like there. Just anyway.
A bit higher.
Go up to turn up. How's that? To be honest with you, I can probably shout in this room, right? Yeah. I've got a pretty loud voice anyway.
It's clear now, at least.
Yeah, yeah, okay.
Well, apart from the Scottish bit.
Don't let me stop you leaving if you want to. Okay. So the very first, although I've done some messing around with computers and mainframe computers in university, so we got a little bit of time from school and all this kind of thing. The first computer that I actually really got my hands on was a thing called the ZX80. And I went to quite a good school because my dad was in the military and they paid fees and all this kind of thing. So I hung around with some boys who are parents with money. And one of them got this ZX80 thing, and we'll talk about that in a little bit. Then, as I left school, I got ZX81 with the 16K Memotech RAM pack, which is really important. We'll come back to that later. And then, basically, I was on the dole, which lots of people were when I was that age. And I just sat in the house and messed around and disassembled ZX81 games. And eventually got a job with a company called Imagine Software about 7 months before they went bust. but I'm sure the two aren't related, right? And then I was redundant again for a little bit, and then I worked for a company called Ocean. Oh, and at this point you'll have noticed, so I started in 1983, and eventually around about 1985, 1986, I actually started to produce stuff, as opposed to just drinking a lot, smoking a lot of cigarettes, and eating lots of burgers and stuff like that. So this game I did for Ocean Software is a thing called Ping Pong, and I'll be showing you that a bit later. Then I went to work for a company called Odin Computer Graphics and wrote a thing called Hyperball. And then finally, I wrote this thing called Plod, which stands for Planetary Law and Order Department. But really, it's a Northwestern euphemism for nudity, right? Which we thought was just hilarious. I was young. And that was never released, which is probably a good thing. Okay. So, but this ping pong thing was a crash smash. So I'm kind of qualified to talk about this, right? Because if you're a Spectrum guy, crash smash was the be-all and end-all, right? Because Crash was a big magazine. Okay, so what am I going to talk about, and a little bit about why. I'm going to do some nostalgic stuff, because James did say do some nostalgic stuff, but try not to do too much. And fundamentally, I'm going to be talking about software, right? We're always talking about software. It's what I've done my whole career. And I'm also going to talk a little bit about passion, and about complexity, but the flip side to complexity, or the related side to complexity, is simplicity. Okay. Cool, so that's kind of what we're going to talk about. Oh, and I suppose the main message, which hopefully you'll see as we go through the 45 minutes, is that a lot of the things that I learned when I was a ZX Spectrum programmer really helped me out today, right? I think people who did this kind of thing are in a much better position when they're developing software, because some things are just always true when you're developing software. I'll try and talk about some of those things. So, here's my personal computer history. So this is this thing that this guy at school had. The Sinclair ZX80 came out in 1980 and it cost 70 quid, and it had 1K of RAM. You'll notice that most of the CPUs that you're going to see are Z80, because I'm a Z80 guy, and we'll come back to that. It had 32 by 22 character black and white display, okay, so 32 characters across, 22 down, and 64 by 44 graphics. If you look at this number and how it relates to this number, what it means by graphics is you had different characters which had the four-way grid, and that was your graphics, right? So different bits of the 8-character block were filled in. It had no sound, and it only had a thing called fast mode. Now, I should have probably demonstrated this. But what fast mode essentially meant was, when you were typing in your basic program, every time you hit return, right, the screen would kind of flash, right, and then come back. So it didn't do screen refresh, right? Your program went off and it ran, the screen went blank, and then it would come back later with the results, right? And it was hideous because it just flashed at you all the time, right? Horrible. But they sold 70,000 machines in a year, which is pretty good, right? Predominantly because it's cheap, because people, accessibility. I mentioned here the importance of milk and peas, which might not immediately be obvious unless you actually had one of these things. This thing overheated like a bastard, right? And it would overheat really, really quickly, so you could never get anything done. Now, when you're loading things from cassette tape at really low rates, and they take a while to load, and then this thing would overheat and just reset, it's just a pain in the neck. So what we'd do is we'd take, originally we tried milk, cold milk cartons placed on that little lump at the top, right? But then what we found worked out really well was putting a bag of frozen peas on the thing. So we'd be sitting in this boarding house at this grammar school with a packet of frozen peas on a ZX80. Insane. So pretty soon I wanted a computer of my own, and what I really wanted was something like this. This is the Sharp MZ80K, and related 65 to 02 ones are things like the Commodore PET, that kind of thing. But what I really liked about this, right, was it had a keyboard. This previous thing, right, had a membrane. It was just hideous, right? Just horrible membrane thing. This thing had a keyboard, had this nice grown-up monitor, and the cassette player was built in. And why that's important is because it would be very difficult to get the right connection for the cassette recorder to your computer, and you would have to load things about 8 times because you could never get them to load. I figured if it was built in, I'd actually be able to load stuff consistently. So I was really excited. This is the kind of thing I wanted, right? This never going to happen, right? No way my parents could afford that. So instead I got this Sinclair ZX81 thing, and I got it for Christmas, and I kind of badgered my poor mother about it constantly. So this was where the Sinclair stuff really started to take off. It's still 1K,
and it's still Z80, and we've still got this 32 by 22 characters, and you can have each character with a different quarter filled in, or all the different quarters filled in. Which sounds hideous, but there were some reasonable games on this, so things like 3D Monster Maze, there was a flight simulator, there were lots of good games came out for this thing. And it added slow mode, right? So it constantly displayed what was going on, which is kind of useful for games, right? Because the game, there were ZX80 games, but they were kind of turn-based, right? Because you said, right, I'll do that, it would flash, it would go off, it would come back and say, this is what happened. It's not exactly entertaining, okay? And this thing sold 1.5 million units, which is just amazing, right? Because it's predominantly a UK thing. Okay? It took a while for them to sell, but this thing really took off. Lots of people have these things. And here I mentioned the importance of blue tap. Up here is the Sinclair ZX 16K RAM pack. Okay? So you can add 16K RAM packs. Now if you look at the shape of this thing, you've got this infamous thing on ZX81s called RAM pack wobble, because the connector wasn't very good. It's completely the wrong shape when you look at it. And you literally couldn't touch the desk sometimes, right? Because what would happen with RAM pack wobble? It would reset, and of course it taking you 4 minutes to load the damn game you were trying to play. It would last for a couple of minutes, and then you get RAM pack wobble. So I mentioned earlier I had a Memotech RAM pack, right? Which was kind of more sensible shape, which went along the back and was lower, and so I didn't suffer from it so much. But this was a proud moment of mine that I didn't have this horrible thing. Okay, now, so at that stage, I'm sitting in the house and I'm hand disassembling games. So the one I remember in particular is a one called Quicksilver Defender. And what I'd have to do this, I'd load the disassembler, I'd load the game, and all of this is off cassette tape, right? And then I would literally get the assembly language instructions out and we'd try and work out what it was doing. This, trust me, is a hideously difficult thing to do. It's a good job it wasn't actually my job, I was just playing around at home, right? But I was just obsessed with this thing, so I could sit for hours and hours and hours and hours and not communicate with another human being, and this is why I never had girlfriends, but hey, it worked out. So, then what happened was, I was playing around in my bedroom, a company called Imagine put in an advert, and they wanted lots of games developers and lots of artists and all kinds of things, because they'd signed a big new deal with a company called Marshall Cavendish, who do those part works, you know, when you buy part one and it has a free thing on the front and all this kind of thing. So this thing was called Input, and it was going to have cassette games on the front. And Imagine we're going to write loads of these things. So they had to take on lots of people quickly. And the relevance of telling you this is, I didn't have a bloody clue. They were just desperate for people, right? So they were trawling up getting anybody who kind of could spell ZX Spectrum, right? So I started to work for Imagine, and I thought I'd go over some of the development systems I used. And you'll notice they're really different to the actual systems we were playing games on. So the things that Imagine used were, this is a Sage 2. There was also a Sage 4, which was for the bigger developers than me, right? Because I was just like this junior guy. Actually, you know what I did for the first month when I worked at Imagine? I lay on a floor with a big bit of graph paper, right? Which had some graphics drawn on it. And I hand converted that to hexadecimal so we could type it in and get this screen layout, which is just ludicrous. We didn't do it like that for long. And then, of course, when we got to the end and somebody typed it all in, it just looked hideous. None of it was right. But that's when you're young and people are giving you too much beer, right? So this thing was based on a 68000 and used this weird operating system that you barely hear about called UCSDP system. And the thing about that was it used P code, which is a bit like Java bytecode, i.e. it was kind of semi-interpreted. But ultimately we moved on to CPM 68K, and particularly Imagine, but all the software companies I worked for, there weren't off-the-shelf tools you could buy. So people would write their own assemblers, cross-assemblers, that kind of thing. And we'd have hardware guys on site who would make up the cables which connected this to the ZX Spectrum. So although I'd never had a ZX Spectrum, it was Spectrum games I was starting to write. And we'd have this cable. So we'd do the development on this because this had a real keyboard and a real monitor and was reliable and this kind of thing. And then we download the code to the Spectrum itself so that when it crashed every 5 minutes, because if you've ever written anything assembly language, right, it's not going to run perfectly first time, so on. We could just reset the Spectrum and just carry on and do it iteratively. Okay. The next thing, the next system I use, right, let's get to the punchline first, right? So James is a BBC Model B guy, but they were only for posh girls and boys, believe me. And the other And the other big problem with them is they have a 6502, which is just ludicrous. But that's not serious, by the way. It's just, there's a kind of Z80 6502 thing. The two never got along together. But the reason I used this thing, so this was when I was moving between Imagine and Ocean. I was doing some freelance stuff at home. Is we could actually make it okay. We could turn it into a proper computer. There was a module you could get, which was a Z80 expansion pack, which meant we could run CPM, and I could have a proper Z80 assembler. And then I went to work for Ocean, and this was by far the best one I used. Oh, I also used that one at Odin as well. This is by far the best one that I used, and I don't remember them ever being popular, but they were super popular software houses, all right? And the reason is because they were really reliable, the keyboard was great, and we had this 3-inch disk drive which could store 380k on a disk, right? Which is just outlandishly good. So you might remember, some of you, that the ZX Spectrum, Sinclair released a thing called a micro drive, right? Which was just, had used tiny little endless loop tape cartridges. And some people did games development with them, but I mean, basically they'd last sort of 5 minutes. I mean, these things had stopped reading. So this was reliable, and that's why we really liked it. Okay, but the computer that's missing completely from what I've said so far, and the main one, is the Spectrum, because this is what I wrote games for. And this is the machine that changed everything. It's now got a rubber keyboard rather than a membrane. Ooh. And it's also 16K without a RAM hack, so you don't get RAM hack wobble. And in fact, you get the 48K version, right? 125 quid, which put it within the reach of a lot of families. So ultimately, they sold over 5 million of these things. Now remember, this is predominantly the UK version of this.
Could have been worse.
Yeah, I'm just wondering what might be next. They're going to love that, man. Right. Okay, so this thing was a massive step on from the ZX81. So you had 48K of RAM to start with. You also had 156 by 192 graphics. So you finally had high-resolution graphics, which obviously is really key for when you're trying to write games. And it also had sound. However, what it didn't have, and this is a really big difference between Spectrum programmers and C64 programmers and Amiga programmers and all that kind of thing, is it didn't have chips to do stuff like sound and sprites and that kind of thing, right? I'll go over the sort of technical architecture if you like, but really it was a really naked, bare architecture, which meant that you had to do everything, but because you had to do everything, you could control everything, kind of thing. So it was like the least layered architecture going, right? Okay, so what's involved in developing ZX Spectrum games? This is a kind of more technical version of Z80 architecture, right? But what I'm going to do is I'm going to skip over this, right? Because most of the time I don't care about this stuff. There's a couple of, the next two slides are really the fundamentals, okay? So you have a Z80 CPU, and it had an 8-bit data bus, but 16-bit addressing, okay? So fundamentally it was an 8-bit computer, but could address the 64K range. It also had 64K worth of I/O ports, which I'll be talking about specifically, and that's about it, right? So you had CPU and memory. Inside the CPU, there's a bunch of registers. So going over these quickly, this program control register says which instruction, which area of memory it's executing at the moment. So it points to the instruction that it's executing right now. So when you do jump instructions and things like that, it would change the program control register so that it starts executing code someplace else. This is a stack pointer, which a lot of people will be familiar with because it's basic architecture, where you can push values onto stack and pop them back off again later. So this is used a lot when you're calling things and you want to return back to an earlier bit of code. You push where you're going to jump back to onto the stack, and then when you hit the return instruction, it pops the address off and it returns back. However, in games programming, we use this in lots of interesting ways. So one of the things we did a lot of was the instructions to push and pop registers onto the stack are really efficient, and it pushes 2 registers at the same time. So you've got push HL, push DE, push BC, push AF. Okay? And now what that means is that you're moving around 16 bits of memory at a time rather than 8 bits, which, and I'll mention this later, in games programming it's all about how quickly you can move stuff. And what we do is, we take the stack pointer, we point it at the graphics data, which is just a bunch of numbers, and we pop them off and then push them back onto the screen. Okay? So it's a really, really efficient way of doing that. This came up in the Oak Table list when me and James wind each other up about Z80 and 6502. The Z80 was very feature rich. It was actually a bunch of people who left Intel who bought on the 8080 and they wanted like a better 8080. So they added lots of different bits and pieces and features. These index registers, there's a whole bunch of instructions where you could point at a memory location and you could, by indexing, it would allow you to step through a table. So you'd have your base address and you could add something to it. And of course, we never used them because they're really slow, right? So it's hilarious that Zilog, who made this thing, put all these features in, and as a games programmer, a lot of the time you're just going back to the most basic stuff because it's the quickest, right? Because instructions which use these registers have more bytes and take longer to execute. I'm going to mention this thing called T-states in a minute. One useful thing is had an alternate set, so you could flip the whole set backwards and forwards. So it'd be useful for saving a whole bunch of values that you're going to use again later. Go and do some work, and you can flip them all back again. But you can see that, yeah, and this thing here is what you write interrupt service routines around, and I'm going to mention them specifically later. Fundamentally, though, you can see it's really basic architecture, right? Because if you think of these as your set of variables, it's not a whole lot you can do, right? This is the most variables you're ever going to have in your application, and you're going to be reusing it all the time. Now, what's really important to spectrum programming is the memory map. Some bits more important than others. So the first block is ROM. So the spectrum came with a ROM, and it had sort of BIOS type functions. Okay, so draw a character, do calculations. It had the basic in it and all that kind of thing. So as a games programmer, some people used them, but it was kind of like a. Remember, this was a long time ago. It wasn't very masculine to use ROM routines, right? Proper games developers didn't use ROM routines, right? Why? Because they're too slow. They save some memory because you don't have to write your own thing, but they're too slow. Because they're general purpose, and they're trying to pack as much into one area as possible, whereas we can trade some memory for speed. Then we have the screen RAM, and then the attributes. So people who are used to the spectrum will know, but the spectrum will know that the colours and the graphics were separate, so that you could manage them separately. Why? Because the colours you could only set on an 8x8 pixel block, right? So there was a colour for each character cell, but there was high-res graphics within the character cells. And then you have a printer buffer, and I suppose the only thing I'd say about that is that when you don't have a lot of memory, lots of people would use the printer buffer to put bits of code in. One of the running jokes in the Magic was the VIC-20 had 3.5K of RAM, right? And it used to be a mark of a man again. I'm sorry, this was so long ago. It used to be a mark of a man that you could write a program for a 3.5K VIC. And these guys always used the printer buffer, right? We weren't quite as desperate. And then you have some reserved areas, but then you have this big chunk of memory that's available to you. Okay. Now, why that's important is that the ZX spectrum is essentially a memory map display. Okay? There's no special graphics hardware or anything like that. All you've got is this block of memory, and when you put numbers there, it's going to read them and it's going to display them on the television set. Because remember, this thing used a television set, so you have to plug it into your mum and dad's TV, as well as have a cassette recorder to load the games. Right. I love this line. It's rather curiously laid out. So when you write your first ZX Spectrum sprite routine, you would assume that when you write a line of data, if you want to write the next line, you write it in the next memory location down, right? So it would be 32 characters across, so it's 32 bytes. I would assume that when I went to the 33rd byte, it would be the next line on the screen, right? Not quite. So what I'll do for this is, let me show you a little demo. I'm so glad I found this morning, by the way. This is the ZX Spectrum game loaded. Now, because it's loading from the bottom of the memory, right, what it's going to do is it's just doing the data sequentially. So you see that the way it actually does it is it does the first line of 8 lines, of 8 character lines, then it goes back and does the second, then the third, then the fourth, then the fifth, and then it goes on to the second third of the screen, and then it goes on to the third third of the screen, and right at the end what it's going to do is it's going to fill in the colours because they came after the graphics memory, right? Now, trust me, when you're writing this thing, it just kind of, your mind boggles, right? So why on earth would they do that? And the simple reason is, because if you think about it, you're doing 16-bit addressing, okay? So you can jump down the line by just changing the high order register, all right? So it's actually quite logical, but it's not logical in the way human beings are logical. It's logical in a way that makes it really efficient to put graphics on the screen quickly. Okay. Cool. But completely freaked you out the first time you see it. Well, everything was going so well. Okay, is that alright? Yeah, I can show you. Now, the really important thing if you're ZX Spectrum games programming, the be-all and end-all of good ZX Spectrum games programming is this thing called an interrupt service routine. Now, the way the Spectrum's designed is, remember, it's displaying data on a TV set, okay? And it has this thing called a ULA, uncommitted logic array, which I think they call ASICs now, right? Or an ASIC is like a better version of a ULA. And it's basically just looking at this memory area and drawing lines on the television set. When it hits the bottom of the television set, you get a thing called raster flyback. So it's now got to go back to the top of the TV screen and start drawing it all again. Now, there's a gap between when it hits the bottom of the screen, the time it takes to go back to the top of the screen, and the top border area. So let me just show you this thing again, briefly. We'll give this an aperture. Excuse me. Let's see. And this noise just brings back memories, right? This is the noise of the tape loading, by the way. That's the noise of the microphone falling. Okay, so between when it hits this point, at this point it triggers an interrupt, okay? So it's a hardware interrupt, so you know I'm at the bottom of the screen. Now what you've got to do is you've got to draw as much as you can while the raster's going up, and in this top area, and in this border area, right? So it flies up, and it's drawing the border here. What you're trying to do is to not be drawing stuff on the screen when the raster's going across what you're drawing. And it's a really, really critical part of Spectrum games development. So what we're doing a lot of the time is we're just shoving as much data into screen memory as quickly as possible. So we've got the graphics in our memory areas, right, where the application's running. We're just trying to move that stuff into the screen memory area as quickly as possible so that we don't have the raster going over while you're drawing the graphics. And the reason is because if you do, you'll get sprites which flicker. And it's a mark of a really bad Spectrum game when all the graphics are flickering. On a side note, it's also why, once you know this, it's a sort of fun thing if you know Spectrum stuff, you start to understand why it was so popular to put big high score panels and instrumentation panels at the top of the screen, right? Because now you've got the border and you've got that area and then you have the sprites at the bottom. So it's just giving you more time to draw stuff, right? Okay, so that's the really important stuff. You've got a Z80, you've got a chunk of memory, and you need to write an interrupt service routine which moves data from one to the other really quickly. And that's kind of it, to be honest with you. So, I thought I'd give you a few examples of some actual things I did. And it's just kind of fun, but it's just some little tricks and stuff. So this, I did have a nasty habit of developing things which never got released, right? If you buy me beers later, I'll explain some of the stories behind it. But this was quite possibly the best thing I ever wrote, if I'd actually finished it, right? This was the thing that got me the job at Ocean, and it's the thing called Grog's Revenge. Has anybody heard of kind of like, there was a whole C64 series of games, right, about this cartoon character. And what this had to do was do left and right scrolling across a big area of screen at different speeds, so 1 bit, 2 bits, 4 bits, 8 bits, and that kind of thing. And this was the thing that got me the job at Ocean, because I went to demo it. Man, I throw stuff away, right? You know, you get people who hold stuff and people who throw stuff away. I throw stuff away. To my eternal discredit, I don't have any of the source code I wrote for this stuff, right? And especially not unreleased stuff, because it's not been put out on the internet. But this was by far the best individual thing I ever wrote. Super smooth, and it kind of varied in speed and all this kind of thing. And when this guy called Joff, who I'm going to mention later, saw it, so they said, show us this thing you've got, and he was blown away by it. So, one of the things I'm most proud of, apart from the fact I didn't finish it, So we got to draw large areas of the screen. Now there's this Z80 instruction called load with increment and repeat. Okay? And what that does is you set up a couple of registers and you say I'm about to copy from here to here. All right? So one set of registers used as the counter, one is as the source of addresses, and one's the destination addresses. And in a single instruction, which is cool. Remember I said Zilog added all this cool instructions. In a single I'm sorry. Maybe I could just, yeah, actually I better keep quiet about what I could do with it. Or do with myself. Now, in some ways it's a really cool instruction, right? Because just in one instruction, it doesn't use up memory, we can say copy loads of data from here to here. The problem with it is that it takes, so I mentioned these things called T-states. They're not strictly clock cycles in Z80 world, but T-states are a way of comparing the relative time that instructions take. Okay? So for any given Z80 instruction, it takes a certain number of T-states. Lower is better. So this load with increment and repeat, most of the time, when it's doing the repeating, it takes 21 T-states. When it gets the very last byte that's copying, then it takes 16 T-states, because it's not going to loop round anymore. However, there's also this instruction called load with increment, which takes 16 T-states all the time. But clearly we have to loop round, right? So I need to factor in the time to do it. So I thought, what would be really cool would be if I could use LDI instead of this LDIR thing, and get 5 clock cycles, right? How did I do it? And I know this looks hideous to modern eyes, right? All you do is you have a whole bunch of LDIs, followed with some logic at the end, which jumps back when the count is set. So you kind of write your own thing. You know what? I'm going to leave that up there. Because I've got the cojones to see what this is. So I would just have a bunch of LDIs, sort of wasteful apparently, okay? Just this whole bunch of LDIs with the loop logic at the end. And it's just called writing inline code. And if you look what compilers do, when they're in time-critical parts, the compilers do this kind of thing sometimes, right? But it's not a thing that a developer would do these days, right? It just looks hideously wasteful and clunky. But it gave me an extra 5 T-states times the number of them there were, which I think was 28 or something like that, because I had a border on it. And it made the whole thing go quicker. But just stupid stuff. Very cool, but not something you do these days. Another example, and I wrote a blog post about this, because I think this is super important, right? And it's a really, really well-known thing, which all Spectrum developers did. Oh. Okay. Remember I said that it's really important that the raster isn't crossing the graphics when you're drawing them, right? Because they'll flicker. So the question is, how do I know where my program is at any moment in time to make sure that it's all running before it reaches that point? Or to see at what point I'm drawing a specific sprite so that I can see it above where the sprite lives on the screen. Okay? And if you think about a machine code program, because it's alright talking about assembly language, but essentially it's machine instructions on a chip, right? This thing's already really efficient. So to give you an idea, the screen refresh is 50 times a second, right, on a UK TV. On ping pong, it would execute the whole application with the raster flyback and maybe the top 1/8 of the screen. So the whole application runs 50 times a second, right? The last thing you need is some complex instrumentation because it's just going to screw up performance, right? So you need something which is extremely low cost and non-intrusive. Has anybody got any ideas what we maybe did? Or remembers it? No? Okay, that's good. There was a bit of technical detail I didn't mention about the Spectrum. Man, this kind of, it blows away the Commodore 64, all right? Because what we had is memory, a CPU, and woohoo, we had an input-output port as well. There's no sound chips or graphics chips, but there is an input-output port, one, which is used for 2 things. So in terms of input, it was used to tell when people were pressing keys on the keyboard, all right? In a really complex mapping, which was just hideous. And it kind of made sense as a cheap way of doing it, but it wasn't easy to work with. And then we have, when we use the port for output purposes, we basically have, we can set a bit to put something out to the speaker to turn it on and off. So you do 1, turns the speaker on, makes it go click, and 0 makes it off. Same with the mic input, you can read stuff in. And then we have 3 bits there for the border colour. Okay, so it can be 1 of 8 border colours. So this thing? Yeah. So essentially, all we did was we changed the border colour, because it was a single output instruction, and that's what this thing is doing, right? Is it's just executing one instruction which says change the border between blue and red, and between blue and yellow in this case. Now as you see, because of where it's being changed, the lines move. Now this isn't a great example. Let me tell you, you're not going to find examples out there of what we actually did, because we take the instrumentation out before we release the game, right? But let me try and describe the way you might be able to imagine. These border colours we changed at different points, so we could see where a sprite was being drawn based on the colour, and there would kind of be this moving instrumentation picture. So if you're familiar with response time profiling, like the Kai Millsap stuff, right? This is kind of coloured response time profile, because it shows you by the thickness of the colour where you're spending your time. Does that make sense? A lot of blank faces. No, you're just bored of your. So that's how we do that. Oh, I love this. Now this is completely for fun. This is just utterly for fun. You know how these days when people leave the screens unlocked, okay, so I work in an office, and I've just got this. This has lasted with me since I was 17, right? As soon as I see a screen unlocked, I have to sit down there and chat with mates, and I love you guys, and send ridiculous emails to senior people and all this kind of thing, right? It's just fun, right? So the ZAC equivalent of this, and this is how obsessed we are with performance, is if somebody went out to the pub at lunchtime and left the screen unlocked, okay, we would go through the code and we would look for anything at load A0, right? And the reason is because this takes 7 T-states, but this exclusive OR A, which does the same thing, because if you exclusive OR something with itself and makes it 0, is only 4 T-states. So we'd literally go around changing guys' codes, right? Replacing this with this, and then putting comments and clown you idiot and this kind of thing. Just for fun. There's no intellectual purpose there. Okay. So one of the things I most admired wasn't something that I did, but was the ping pong music. Okay. So at the time, although it was on an Imagine label, I was working in Ocean, so I was in-house developer, and I worked with this young guy called Geoff Smith. And his game wasn't ready to ship, and my game was ready to ship. He also had memory problems, and I didn't. So what he did was, he was good enough to say, look, I've been working on this really cool music thing, you can have it, and just let me plug it into the game. Okay? So he wrote, this is very Geoff, right? Plot music programming, which might make sense when you hear it. But, and this guy, Martin Galway, wrote the actual tune. Now here's the thing I want to emphasize, it's really important. All you can do on the spectrum is flip the state of that bit to make the speaker go on and off. Right? Now, there might be a lot of surrounding code, believe me, there is. I didn't write it, right? Some clever guy wrote it. Fundamentally, taking this one simple switch on, switch off, because it's all he could do, right? This is what he came up with. And it's the instructions there, the 12 T-states thing. Now, at this point, I could also, you know what I really love for a guy who doesn't board stuff? Because these days, you have a thing called the internet. And you have things called emulators. So this is the ZX Spectrum emulator. And what I'm going to do is I'm going to open a snapshot, which you can get online, of my game. So even though I didn't board it. Now, I know it sounds dated, but nothing would be done like this, right? And what you need to remember is it's just some guy with a little bit of memory and some guy writing a tune, flipping a bit on and off, right? If you listen to it, sound chips have channels, right? So you could do percussion on one channel and tunes on another, right? This is not got channels, he's creating channels, if you like. So you've got the little drum beat thing, and then you've got the synth thing going on, and all this kind of thing, right? So, trust me, when this came out, people thought this was just amazing, right? I'm going to stop you going to listen to any more of it. Not least for reasons of time. So, most of our games got reviewed in the same edition of Crash, right? And mine's got 90% and his got 88%. And when you actually read the reviews in any real detail, they're all like, the music on this thing is amazing. So that's what I call a proper friend, right? Because he gave up his Crash Smash and let me use his music. Okay, so I wanted to try and focus on a few lessons learned from all this. Okay? And what I mean by this is, I constantly think that, and lots of table guys and girls and stuff would tell you this, we do tend to whine about the current generation of IT people. Not all of them, right? There's amazing guys. Some of my best friends are young. Yeah, that was a joke. Nobody young would hang around with me, right? But I think sometimes that people haven't had the right grounding, right? Because they haven't had to deal with really sort of building your own stuff, right? So they don't think about efficiency, because these days you don't have to. If you think about that emulator, right, you should see how much we have to slow down that emulator, because it's running on a modern PC. If you get a ZX Spectrum emulator on a modern PC and you don't have lots of delays in it, it all flies past you, right? Because everything's so bloody efficient compared to modern software. Now, it's kind of good that we don't have to be that efficient, right? And we're not reinventing the wheel and always writing the machine code. But I do think it's nice to have done it at one point, because you always have this mindset that efficiency is important. I'm going to steal another line from somebody else. It's Alex Gorbachev at the back, and Tana Opoda, sorry to draw attention to you, and correct me if I'm wrong as well. Often mention the fact that the reason there's so many great software people from the Eastern Bloc is because when you're a kid and your toys turned up at Christmas, you had to make them work yourself half the time, right? You've said something similar to that, right? So these guys were used to playing with things and fixing things, right?
I think it was because they were standing in line constantly, having a lot of time to think.
I knew I could rely on you to insult them more than me. So efficiency is still a good thing, and I still think in terms of efficiency, even though I don't need to write code that's as efficient, I don't need to go into machine code or C for everything, you should always have at the back of your mind. And the thing that occurs to me, if you look at what I'm doing in the office right now, all I'm doing is writing something which moves data around quickly. And if you think about it, a lot of times database people, you're just moving data around quickly, you're just trying to make that efficient. Now, whether that's moving blocks of memory on some old 8-bit computer, or whether it's on some high-end server, we're still focusing on how can we move data around quickly, and efficiency and that kind of thing. Performance analysis always depends on good instrumentation, and the reason I wrote the blog post about changing the colour is everybody talks about, well, developers don't understand instrumentation. That was 1986, for God's sake. How long is it going to take people to get the fact that you have to instrument your code in order for you to know what it's doing and where you're spending your time? Because sure as hell, eventually you'll get a performance problem, and instrumentation is the only way you'll be able to get to the bottom of it, right? But it needs to be appropriate to your solution. So because we were writing really low level, we didn't have much memory, and we wanted something non-intrusive, we just changed the border colour. But there's all kinds of things like that you can do. I sent a link to that blog post to Carrie Millsap, who's really interested in the instrumentation and response time profiling. And he told me about an example where a water company worked out what was happening with water flow by putting 2 different coloured dyes in different sources. So they wanted to know where the water was coming from. Whatever it is, whatever suits you. Now, one of the things that people always thought that ZX Spectrum programming was complicated, right? So machine code, it's hard stuff, right? Assembly language is really, really hard. But actually, I always thought it was a little bit easier, because if you look at Z80, it has a lot less instructions than you have Java class libraries, right? If you look at the Oracle documentation, it's just hideous. It's all the stuff that you have to learn, right? If you're actually restricted and you've only got the instruction set of a CPU, what you're doing is you're taking some really simple stuff and building up something complex from it. And you'll learn a lot from doing that kind of thing. Because if you think about it, some of the most simple things, right, just individual blocks. This just hit me while I was in the pub the other week, right? I know what it did. It's the kind of thing which pops out with beer. If you think about it, there just aren't that many musical notes, right? And even when you combine them and you start having chords, there aren't that many. But think about all that music that's been out there, that's been made from just these really basic building blocks. And it's a similar kind of concept. Oh, I know it's not a technically accurate atom picture, but if you think about it, it's like building up atoms to build something incredibly complex. Okay. I wanted to say quickly a word about this. Is this guy, Joffa Smith, right? He was just a coding genius, man. And it's a little bit sad that I'd have to say, so I worked with him when I was like 19, 20, that kind of thing. I've never worked with anybody nearly as good since, all right? This guy was off the scale. He changed quite a lot over the years as he got into clubs and other stuff, but and he just wrote tons of games and stuff. This guy was just ridiculously prolific. Sadly, he sort of passed away a couple of years ago, so I just wanted to give him credit. But what I think I got most from the ZX Spectrum thing, right? And what I think, and I'm going to whine, what I see missing in people I work with them, not all of them, I work beside a young woman at the site where Dawn and I both work, and she's amazingly passionate and really gets it, is really into IT. But there's a lot of passion and dedication missing in people who are getting into IT now, because they didn't get into it because it was fun and it was the hobby. They got into it because it's a good career to go into and you get paid lots of money, right? And they're kind of missing something because they've never had the passion. But it's good signs. People know what this is, right? So this is a Raspberry Pi thing, which is 27 quid, right? And if you look, this is a USB port, right? So this tells you how big this thing is.
That's an HDMI port.
Sorry, that's an HDMI. Smart. Which one's the USB? Those?
Yeah.
Yeah, okay. Because the thing is, nobody has to program anything these days, right? If you've got an Xbox, one of the things which me and Geoff really struggle with is games programming is nothing like this anymore, right? Because it's this multi-million-dollar thing and you have massive development teams. Geoff went clubbing for a while, then got back into games, and he walked in and he was like, why do you need all these people? You know? So games development is a hideous thing now. It's just as bad as every other area of software development. But what we really need is for kids to be playing around with something which just doesn't deliver everything they've got. So hopefully, I'm not convinced with the kids I know, including my daughter I might add, that they're going to give us stuff, but we've got to try and get people more interested in things. And as I can see, cut the dude guy at the back, and I think I'm about on time. Yeah, that's it. Thank you.
Thank you.